Alright, this is G3 with double slit interference or two source interference of waves, and this is going to be similar to our single slit but an extension. And so let's recap the single slit, or what is superposition and interference. Well, anytime you have waves that overlap at the same point, it's called superposition, and we can see either constructive interference or destructive interference. Constructive interference is when we have crest and crest that produce another larger crest, or trough and trough to make a bigger trough. Destructive interference involves a crest overlapping a trough and giving us some kind of cancellation. It may not be zero, but typically it's closer to zero. And for our single slit diffraction, these are slides from our last option. We see the wave fronts doing this and giving us an interference pattern where the central maximum is the brightest and then your subsidiary maximums are way smaller. That's a single slit diffraction pattern. Now let's take a look at double slit. So with a double slit, in other words, we've got two holes in the opening, in the wall, and our wave fronts come in perpendicular to the boundary, but they're parallel to each other. And then you see, and I guess I should make this one blue, because it's through the top hole that you see the blue wave fronts that expand out, just like we saw previously. And then through the bottom slit with the red, we see the red go through and spread out. We see diffraction through each. Now, it's the overlapping of those two diffraction patterns that we get our interference on the screen. And so you'll notice where you have a crest and a crest, these are going to be constructive interference, and then a crest with a trough, which is the space in between, would be your destructive interference. Well, put it all together on your intensity screen. Okay. Here's another picture, a three-dimensional picture of what's going on, and you'll notice you get bright areas here, here, and there. If this were sound and you had loudspeakers, we actually did this demo, I think, without the microphone, but you'd see areas of loud, soft, and loud. It's going to be loud when it's straight in the middle across, and then you would have areas of soft above and below, and then loud above and below that. And we'll get to a picture of the intensity pattern. It's somewhere in here. But if you look back at our interference patterns, maybe it's on the next slide. Okay, so here, there, okay, so the slide is in the wrong place. But if we look here, what's happening is we see a triangle from the slit 1 to slit 2, and the angle that's formed is going to correlate to the lambda, the path difference from the two waves. So the lambda here, this would be our first order of separation, or n lambda. And so that path difference is what we're going to take a look at for our equation. So I'm going to go back. Okay, so for constructive interference, we see a path difference of whole number integers. In other words, 1, 2, 3, and 4. When the path difference, in other words, the difference in the distances that the waves have to travel, is in whole number of wavelengths, that is where we see bright spots, or the waves are in phase, constructive interference. This is a review from topic 4, actually. And then when the path difference is half a step or half an interval different, that's destructive interference, or that would be a dark spot. And it says it's 180 degrees out of phase. Okay? So that's the path difference review from topic 4. Oh, and note that the two wave sources need to be similar in their amplitude in order to observe the interference pattern. If they're different, it's not going to be visible or it's going to be fuzzy. So we always assume that they're similar in amplitude. All right, the most famous experiment for double slit interference is Young's double slit experiment. And what he did, he had a lamp, okay? He started with a lamp on the left-hand side, and it's not coherent, and it is unfiltered, unpolarized, and then it was allowed to pass through a colored filter. And what this did, it made it monochromatic. Only one frequency was allowed to pass through. And then it passed through a single slit, and it had its own central maximum, and that way it was then coherent light. So now we've got coherent monochromatic light passing through our double slits. And what this produces are the double slit interference. And look at the next slide to see the pattern. I'll come back. Here's the pattern that we see through a double slit. Now remember, in single slit we had one central maximum. Here we still have a central maximum that's the largest, but all the others gradually decrease. It's not that dramatic decrease that we saw with single slit. And even more so, here's a picture you'll see where they're even intensity. So we're looking at it sideways on this one. They are even in intensity. You only get this when the slit width is assumed to be negligible and the fringes are equally bright. You'll see both patterns when you look through the textbook, but this one's actually the more common with IB. We make that assumption, and so we have equal intensities. I want to go back to this one, and it shows, you know, the waves, and your triangle would be right here. There would be your angle. Okay. Anytime you have the maximum, it's a difference of lambda. So if it's your central maximum, that is order, or n equals 0. Your next maximum would be n equals 1. And it's on top and bottom, because you see the same effects on top and bottom. It's not a positive or negative 1. It's just n equals 1. And then your second subsidiary maximum is n equals 2, top and bottom. And it says down at the bottom that n equals 2 is meaning it's a path difference of twice the wavelength. All right. And there's a couple simulations here, so it doesn't mess up the video. You can go to the PowerPoint and click on these and play with these, but both deal with double slit interference. The first one is a ray gun. The second one actually allows you more control in terms of changing things like color, slit width, and the distance from the screen. So the second one is more educational, but the first one's a good, intro. All right, so some equations. So going back to this picture, and this is for a maximum, you notice a lot of variables. And the variables that are important in terms of equations, capital D is going to be the distance from the slit to the screen. And so that is, how far it has to travel after it has diffracted. Lowercase d is the slit separation, and we usually go from center to center. Whatever you use and you're consistent, that is your slit separation. It's similar to your slit width whenever we had single slit, but now that we're double slit, it's how far apart are they. And then x is the distance from your central maximum, which is here in the middle, okay? Here would be n equals 0, to the first subsidiary maximum. So here would be n equals 1. Now these variables are very important because notice they're all some kind of distance. Watch your units because the wavelengths are usually given in nanometers and your slit separation is usually done in millimeters. Your length or the distance to the screen is usually in meters, and then your fringe separation, or and by the way, the fringes, those are your maximums. Okay, the distance from one fringe to another would be, I think it's usually in millimeters as well, or centimeters, either one. So just really be careful with your prefixes. Make sure you don't have any conflicts. Convert to meters is what I like to do. All right, so this is leading us up to the equation. And so the equation, the first one that's in the data booklet, is just the trigonometry. Sine theta is your lambda over the separation of the slit. Okay? But then if I combine it with your distance to the screen equation and your fringe width, I actually can get, and assume small angles, I get this bottom equation. This one is also in the data booklet. It just looks a little different. They have it actually, I think, in this form. It's the same thing. It's just what does it solve for? In fact, in the data booklet, they go in and throw in the order or the n number. Is it n equals 0, n equals 1, n equals 2 in front of the lambda. So that's how you would see it on the data booklet. Both equations are used for diffraction. It just depends on what you're looking for. If angles are involved, you'll use the first one up top here, middle. If there's no angle and you're just interested in the distances, you'll probably use one of the last ones. And this slide actually shows what the slits are the same, the links to the screen are the same, but we've changed the wavelength or the frequency of light. And so as you notice with red going to blue, the fringe separation decreases. So you could say as the wavelength, red has a larger wavelength, is larger, your X or your fringe separation is greater as well, it looks like. Just how color, the PhET simulation will allow you to play with colors as well. All right, that's G3. Check out the next video for G4.